Yes, thank you, Nathaniel, and welcome everyone to this talk. I will be talking about finding memoryless POMDP policies, and in particular, I will be talking about the complexity of doing that. This includes work, and now this is very embarrassing, of course, because somehow two names dropped off this list. But this is including work with Niels Jansen, Joost-Pieter Katoen, Guillermo Perez, Tim Quatman, Wimma Tobias Winkler, Leonor Wintera, and Becca. And the outline of the talk is actually two steps that we will discuss. The first, I will relate we'll discuss what MDPs and memoryless policies on them are, and I will relate them to parametric Markov chains, all of which I will introduce in a bit, and then we'll discuss them a bit more and relate them to the existential theory of the reals, so that we end up with a statement that solving POMDPs or finding memoryless policies in POMDPs is existential theory of the reals hard and complete. This talk will be mostly graphics. So if you want to have a look at the formal treatment during the talk or afterwards, I would recommend looking in one of these two papers. So yes, my screen just went off. You seem to be still there. Yes. So let's start with a small puzzle. You've probably seen this before. This is a Monty Hall problem. You're in a game show, and there is a car and two goats, and they're randomly moved to each door. You cannot see them, and you want to win the car in this setting. And the question is, how does the game proceed? Well, you're going to pick a door, and then the game show host says, "Well, do you maybe want to change the door?" And then, for example, you will open the door. You'll see there's a goat, and you lost. And now the question is, how do you win this game? And my proposal would be that you change the door if the car is behind the door that you didn't pick. Oh, sorry, I explained it wrong. Let me. So the game master. Sorry about this. It's still early. The game master opens another door and now asks you whether you want to switch, yes or no. And my proposal would be that what you should do is you should switch doors exactly if you initially picked a door where there's a goat, because then if you will switch, you will win the car. And if you initially picked the door with the car, then you should not switch, because you will switch to a door with a goat behind it. But this proposal is, of course, silly, because you do not know whether there's a car behind the door or not. So that proposed strategy depends on unobservable information, and that's a very common issue in sequential decision making, that you want to make decisions based on information that you cannot observe. And the Monty Hall problem is also notoriously hard. So even for trained mathematicians like Paul Erdős didn't believe that it's actually always better to switch the door. And we will do a bit more analysis of this in a bit. So I claim that you can model this as a partially observable Markov decision process. And the outline of that model looks as follows. You start in some initial state. And then with uniform probability, you go to either of these three states, which are only, the car is behind the first door, the car is behind the second door, the car is behind the third door. Going to draw that like this. And then what happens is you have three action possibilities. You pick the first, the second, or the third door. If you pick the first one, you do it correctly, and in the other two cases, it's not good. So this is just a labeling. And then I'm going to aggregate some states. But roughly, the POMDP looks as follows. In every state, there's one action which brings you to the state where you guessed correctly, and two actions where you guessed wrong. And then one of the doors with a goat is opened by the game master, and you can again take an action to switch or not to switch. And if you do not switch, if you guessed correctly initially, then you win, and otherwise you lose. And in the other state, it's exactly the same. So this is a Markov decision process. You see the ingredients of states, distributions, and actions. And now the problem is that you want to find an action which does not depend on the state that you're in, because you do not know in which of these states you are. So you have to pick one of these actions 1, 2, 3 in every of these states. You can also decide to randomize over them, but you have to randomize the same way over them. And then you can select to change to switch or not to switch, but this again has to be independent of whether you are in the left or the right state. And as a spoiler for what comes later, it doesn't help you to recall what you did before. You might recall that earlier you picked the first door, but really that doesn't help you in your decision to switch or not to switch. So is this always true that memory does not help, and are POMDPs always that easy? Let's look at a slightly different example. This is this famous cheese POMDP. I don't know why it's called cheese, but that's its name. And here, this is a small maze. And what you want to do is you want to reach the state with the red flag. You do not want to be eaten by the dragon. And the only thing that you can observe in the maze is basically whether there's a wall or not a wall between these tiles. So you for example, in state 2, you can go west or east. You cannot go north, and you cannot go south, and you observe exactly this information. And then what you get is this set of observations, and importantly, the states 6, 7, 8 share the same observation, and the states 2 and 4 share the same observation. And now let's assume that you start randomly in state 1 or 5. Then you can reach the red state with probability 1. And what you need to do is you have to randomize into 4. So for example, it's obvious that from state 3 on, once you're here, you can go south 2 times and you will reach the red state. And now if in state 2 and 4 you just uniformly pick to go either west or east, you will with probability, you might visit state 1 every now and then, but if in state 1 you go east every time, you will always go back to state 2, and eventually you will go to state 3 and reach the red state, and the same will work from state 4 on. So here randomization does help. That's important to notice. But that's not always sufficient. So for example, if we start in state 6 or 7, there is no memoryless policy which will bring you down here. Why not? Well, imagine that you start in state 6. You know for sure that you can never go south. And because we are looking at memoryless policies in the same observation in state 7, you will then also never go south, and that will prevent you from going reaching the red state ever. So in general, you do need memory, and if you restrict yourself to memoryless policies, then randomization may help. Now, so this is kind of the introduction to this thing. I want to take things a little bit more slowly now. and also be a bit more formal. So let me start with a recap what a Markov chain is. This was back in the age where you still needed to travel to work rather than just roll out of your bed. So what happened was you have a Markov chain where there's a set of states, for example, that you're asleep or that you're having breakfast. And once then there are events like an alarm goes off, and then there's a probability distribution to which state we will go. So with probability 0.9, after the alarm goes off, I would go to breakfast, and with probability 0.1, I would just sleep in, and then I would definitely not make it to work at 10 a.m. And then I would take my bike, and most of the days that would be sufficient to make it in work in time. And the interesting question would be, what's the probability that I reach this state, for example? So these are Markov chains, Markov decision processes. They extend this by allowing multiple events or actions. So for example, I could just also choose initially that I'm going to sleep in and not even put on my alarm clock, then I will definitely not get to work in time. And after breakfast, depending on the weather, I could either choose to take the bike or the bus. And depending on whether I would take the bike or the bus, I would get to work with in time with different probabilities. So these are Markov chains and Markov decision processes. And in the remainder of the talk, I'm assuming that the number of states and the number of actions here is always finite. Then the last model, finally, POMDPs. POMDPs are now partially observable Markov decision processes. And for this talk, it suffices to think of them as Markov decision processes where every state is labeled with a color. And now the key question in Markov decision processes with or POMDPs is you get such a sequence of colors. This is what you observe from the system, and now you have to select a distribution over the actions that you can take. So initially, you only see a blue cycle, and then you have to select a distribution over A1, A2, A3. Then you might see now we're in a green state. You have to select the distribution over A1 and A2. Then you again see a distribution over A1 and or a green state, and you again select a distribution over A1, A2. And one of the important questions, if you have such a POMDP, is the question whether there is such an observation-based policy such that you will reach a red state, which is maybe somewhere over here, with a probability of more than lambda. Sadly, this problem is undecidable. And then there's this very nice quote from the Artificial Intelligence, a Modern Approach book, where they say, well, but we cannot avoid using POMDPs as the real world is a POMDP most of the time. And so indeed in operations research in AI and recently more and more in verification, people are looking at solving this problem with some approximations. Let me say that even the approximative version of this problem is still undecidable. But so what people either do is they look at something which is called belief controllers, where you transform your POMDP into an infinitely large Markov decision process, or you look at somehow making some abstractions, and then you try to find finite state controllers where you the policy that you're encoding with them is limited in its size, and the problem becomes decidable. And we will be looking at a very special case of this lower part, that is the question whether there is a memoryless strategy or policy such that you reach the red state with a probability of at least lambda. And a memoryless strategy here just means that we're going to reactively map colors to distributions of our actions. So in every state, we're just going to, my screen keeps turning off, sorry for that. In every state, we're just going to select an action with a particular probability. And this problem has been shown to be NP space and NP hard in 2012. And we will improve those bounds in this talk. So I said that we are going to map observations or colors to distributions of our actions. And then it's easy to see that this is the same thing as saying that we're going to map a pair of an observation and an action to a probability, such that the probabilities sum to 1. So for example, whenever we see a green state, we're going with probability 1 minus x, take action A1, and with the remaining probability x, we're going to take action A2. And we can do the same thing in blue states, where we now have a different distribution, which we can describe with variables y1, y2, 1 minus y1, and 1 minus y2. We're going to take these three actions respectively. And so all I'm doing here is a slight reformulation. And now let's clarify that our strategy is now actually uniquely described by these values for x, y1, and y2. So just saying, well, whatever strategy we're going to take, we can actually describe it by fixing what the values x, y1, and y2 are. Oh, that was one button to 4. So now what we do here is we're going to look what happens in the induced Markov chain. So what happens if we apply such a strategy to our POMDP? Well, then, for example, if we are in this state down here, then with probability x, we're going to take action A2, and we will loop back to the green state. And with probability 1 minus x, we will take action A1, and then we will get to this middle state. And importantly, with the same probability x, we will take action A2 here. And then with probability 1/2, we will go to the leftmost state. And with probability A2 times O.5, we will go to this middle state. Additionally, if we take action A1 with probability 1 minus x, we will go to this middle blue state. And so this is the reason why there's a sum here. Just to be sure, can you see my mouse? Okay, great. So really all I've been doing here is saying, well, we know that we can describe our strategy with this value x1, y1, y2. Let's assume for any of these values that we did that, how are the dynamics of the system under this policy? But what we have here on the right now is a Markov chain. So we do not need to think about the colors anymore. And really the question now becomes, are there values x, y1, y2 such that we will reach a red state in such a Markov chain with a probability of at least lambda? And that is nice, because this is exactly the problem of feasibility in parametric Markov chains. So what I just did is I sketched the reduction from any POMDP and the question whether there's a memoryless strategy to asking whether there are values for these parameters in a parametric Markov chain. I will in a bit also do the return way, but because we'll be using these parametric Markov chains as the proof for the ETR completeness, I'm going to be a bit more formal here. So again, Markov chains, set of states, set of distributions. And for the sake of our later argument, this is the Knuf-Yao die, and what we're going to do is we're going to flip coins, and we have two different coins. They're both fair, so it doesn't really matter. Start with the blue coin. We flip a couple of times, and if we reach in one of these states, we can show that we reach each of these states with probability 1/6. Now assume that the blue coin is no longer fair, and you can see that these probabilities are going to change. Now if we are going to do symbolic probabilities, then the question, then these transition probabilities here, they are no longer concrete values, but rather they will be polynomials over this set of symbols. In this talk, you will see that I'm using x and 1 minus x. But what's more important at this point is that you can see that we are using the same probability x in different places. And so if we are interested, I'm a bit surprised by the slide. Let me first clarify, if we have a instantiation, so then we're going to substitute values x for a concrete value and values y for a concrete value. We can do that, and all the occurrences of x become O.6, all the occurrences of 1 minus x become O.4, and then we do the same for y, and then we again have a concrete Markov chain. So parametric Markov chain has these symbolic transitions. If we instantiate that with concrete, every symbol with a concrete probability, we'll get a Markov chain as we know them. And now if we have this question of what is the probability to reach the red state, or is the probability above or below some threshold, then it's important to realize that we have these same values x at different states, which means that whenever we are going to flip a coin and it yields heads with probability x in state 1, then with the same probability x, we will reach heads, we will flip heads in S3. Now, if we're going to make this value, for example, of reaching the red state as large as possible, then you can see that here it's beneficial if x is as large as possible, because we want most of the probability mass to flow to the left branch. However, if we make x too large, then all of the probability mass is going to this state 2. And so finding a value of x that maximizes this, or that brings the probability of reaching this state above a certain threshold is non-trivial. There's a trade-off. And the trade-off depends on the value of y, because depending on how much probability mass reaches S3, the trade-off is slightly different. And so the formal problem statement is now given a parametric Markov chain with some parameters. We want to find a valuation such that we map all of these parameters to a value between 0 and 1, such that if we instantiate this Markov chain, then the instantiated or induced Markov chain satisfies specification. For example, satisfies that we reach a red state with probability at least or at most lambda. Let me now go back to the more informal problem of the POMDP that we reduced to this formal problem I just described about the parameter valuation. And let me finish the cycle. And now you can also see why I use these two coin flips, and with the blue and the green coin, it's very easy to construct a POMDP out of this again, because now what we would need to do is we would say based on the observation blue, we are going to randomly flip the blue coin, and we are going to select the distribution with that we are going to choose to flip heads and choose to flip tails. And in the green state, we can do the same thing, but we can use different distribution. So here it's very easy. We will get 2 actions in each state, and it's easy to see how you get to a POMDP, which is equivalent to the PMC. And this PMC is simple. So roughly it says every probability, these probabilities always occurs in combinations x and 1 minus x. You might also have constant probabilities, and we need to ensure that they always occur in this pair. So the sum of the outgoing probabilities is 1. Well, you can easily translate the PMC in the left to a POMDP. It's harder for the PMC on the right. Why is that? Because here the probability x appears in conjunct with this 1 minus x, but it also appears together with this variable y. And this is something that would be hard to mimic intuitively in the PMC, on the POMDP side. So really what we do is we look only at simple PMCs and simple POMDPs, and then we say, well, you can reduce any POMDP to such a simple POMDP, where a simple POMDP is just a POMDP where every state is of either of these two types. So either you have a non-deterministic choice between 2 actions. This is where we will use parametric transitions x and 1 minus x, or we have single action and randomized choice. And by adding auxiliary states, you can bring every POMDP into a simple POMDP, and this translation is clearly polynomial. This kind of brings the POMDP part to an end, and I will use the rest of the talk to clarify how PMCs are ETR hard or ETR complete, no problem. And first, let me show the encoding into of feasibility into the existential theory of the reals. So the concrete question here could be, is the probability that we reach the red state more than 1/6? And that means that we're looking for variables py for every state and variables x and y for the parameters, such that x and y are between 0 and 1, and where we now can go recursively and say, well, we know already that the probability of reaching the red state from the red state is 1. And by some graph analysis, we can show that the probability of reaching the red state from state S5 is 0, because there's simply no path. And the same holds for these two parameters or these two states on the left. So these variables have to be 0. And now we say, well, if we're in state S4, then the probability to reach the red state is x times the probability to reach the red state from this state plus 1 minus x to reach the red state from this state. So there's a quadratic term here, and we go recursively back and do the same thing all the time. So we always just write it as the weighted sum over the successor states. And we get a set of constraints, and if we take their conjunction together with the fact that from the initial state we want to reach the red state with probability more than 1/6, then answering this question means yes, if the following constraints are satisfiable, and these constraints are in the existential theory of the reals. If you're looking very precisely, earlier I said that x and y should be between 0 and 1. I will come to that, why I'm being strict here. But if you're worried right now, it doesn't matter. It matters. So the encoding wouldn't be correct here. Why wouldn't it be correct? Because I'm using this graph argument for fixing which probabilities are 0, and this graph argument doesn't work if I allow x to be 0 or 1. But we will see that from a complexity point of view, this is not a problem, because I could encode the graph argument into the existential theory of the reals as well. So, okay, what did we just do? We have this problem, and we've shown that we can do encode this into the existential theory of the reals. I want to take you on a small detour before I show you the hardness to show you how we got there. And the basic problem was that when we're trying to solve these parametric Markov chains, we now showed that we can solve a system of polynomials, but this is in general exponential in the number of variables that we need. And the number of variables here is determined by the number of states and parameters, and in particular, the number of states in these problems will typically be large. So people have tried to do better, and the standard and most famous approach for this is to eliminate all the variables for states. You can do that with an idea which you might think of as either Gaussian elimination over the ring of polynomials, or as state elimination as you know it from a non-deterministic finite automata. And what you will get is a rational function like here, which only uses the variables x or that correspond to the parameters. So lots of tricks on how to do that correctly. But the important thing here to notice is that for a PMC, if with a parameters and n states, where all the transition probabilities are linear polynomial as they are here, this rational function on the right can be exponential in k, and this even holds if the PMC is acyclic. So then you will have an exponentially large polynomial. But for any fixed number of parameters, you can do this computation in polynomial time in the number of states. What does that mean? That means that we can, well, first, these functions, don't be mistaken, they are polynomial. That doesn't mean they are small. For example, here is an example that we run on 41 states and 138 transitions. And the result had a numerator which was computed with 408 terms. And the denominator is the product of 48 linear polynomials. And the coefficients, they are absolutely huge. There's a coefficient that starts here and that it hasn't ended at the end of the line. So yeah, this is interesting from a theoretical perspective, but from a practical perspective, this is problematic. Still, what we just did with this state elimination is that we said, well, what you now need to do is you only need to solve one polynomial inequality, which, however, is exponential in the parameters. And this is still exponential in the number of variables, which is exponential, which is the number of parameters now. So we kind of went from an exponential in states and parameters to doubly exponential in the number of parameters. So did we make the problem easier or harder? Like that was basically the point where we started this, and let me now come to the main result. So existential theory of the reals can be thought of as a complexity class. The little recap of the complexity landscape that is relevant here is that we have this p time down here, and then there's NP up here. Famous complete problems are, for example, p time, whether a linear program has a feasible solution, and for NP, whether a Boolean formula has a solution. And then the existential theory of the reals is somewhere between NP and P space, and famous complete problems for that are: given a polynomial, does it have a real root? Or given a set of polynomials, do they have a common root? And just like you have ETR can be thought of as NP over machines where you can store any real number in constant space. And so if you need to guess a certificate, it suffices to, like, if you find a solution with some real numbers in it, it's easy to check whether this is indeed a solution. if you can efficiently handle real numbers, that is. But it's hard to find this solution, just like it holds for NP. And so indeed, there's also the same correspondence that there's co-ETR, which can be thought of as an extension of co-NP. So how difficult is parameter synthesis really? It depends. And in particular, it depends on the relation that we're using. If we're using a non-strict relation, then it's ETR complete. If we're using a strict relation, then it's NP hard, but and an ETR, but we cannot show ETR completeness. But that this becomes clear in a second when I clarify the ETR completeness proof. So again, this is our problem that we are looking at, and we've already shown you that this is in ETR. There's a result that that this problem of given any polynomial, is there a valuation such that the value larger than kappa is ETR complete. And now what we're going to do is we're going to reduce this problem from here. And so how do we do this? Let's take this. I'm going to do a proof by example, and I'm going to use a trick that Fancy Chonev put forward. Let's look at this polynomial, and I'm going to reformulate that in 2 steps. The first one is that any term with a negative coefficient, we're going to rewrite into an extended term. And these extended terms, they are products over the variables x and y, and 1 minus x and 1 minus y. And I can do that in such a way that we get a positive coefficient, but possibly a negative constant term. And now I want to get rid of the negative constant term. So what we do is we just move the negative constant term to the right-hand side. And now what we have is a polynomial over extended terms where all the coefficients are positive. Then we can rescale this by such that all the coefficients on the left and on the right are between 0 and 1. And such that on the left-hand side, all the coefficients together are less than 1. And once I've done that, we can construct this Markov chain, a parametric Markov chain, where you can now read off, for example, the first term, which is 2/8 times 1 minus x times y. And this corresponds exactly to this first path. And notice that any probability that I did not, or any like any missing transitions here, would go to some sync state in order to make this a symbolic Markov, a parametric Markov chain. And so really every term, it just now becomes a path here. And then it's kind of clear that the probability to reach a red state is just the sum over the paths that lead to a red state, and this is exactly the polynomial on the left by construction. And this also clarifies why, well, at least why it's not obvious to get the ETR completeness result for the strict larger, because the variant with a strict larger here is not known to be ETR complete, and it would be a breakthrough to show so, because with only the strict inequalities, you're missing some expressive power. Let me look how I'm doing. Time, yeah, okay. So the landscape looks a little, can be extended in several ways. For example, I said that often you have only a small number of parameters, and indeed the construction that I showed you before can help to establish that this complexity is in P for any fixed number of parameters. Because look here, the problem of solving a polynomial inequality is only exponential in the number of parameters, and it's exponential in the number of variables, which corresponds to the number of parameters. If I fix the number of parameters to be a constant, then it's no longer exponential. You can also think about parametric MDPs. Recall from the start, MDPs were this simpler setting of POMDPs. So we are looking again at memoryless policies, but that suffices for MDPs, and ask whether there is a valuation of the parameters such that for any strategy or policy, the induced Markov chain will satisfy a property. And then this becomes ETR, complete independent of the relationship here. In particular, the fact that this is in NP in ETR follows from the ETR encoding that you get by extending the standard LP for MDPs into a formula of existential theory of the reals. And if we look at the case with the a priori fixed number of parameters, then we can show that this is in NP. So this is this will be strictly easier than the case with the arbitrarily many parameters, but we haven't managed to show that this could be in P. And the main problem is that here we could eliminate all the state variables in the Markov chain, and we don't know how to do that in a parametric Markov decision process. So we don't know whether this is in P or not, and I really don't have a clue, although we thought about this quite a bit. Then I would like to quickly go over this notion of graph preservation that you will see if you look at any of the practical tools for parameter synthesis. They will all assume this notion of graph preservation. And this graph preservation notion is important because it simplifies to select whether the probability is 0 or not to reach a state. Let me illustrate that here. So, for example, we have this Markov chain here, and x assigned to 0 is not graph preserving. And you can see that the graph simply changes if I assign x to 0, and the same happens for x assigned to 1. This is another instance where you can see that x assigned to 0 is not graph preserving. The graph changes. Why is that often a problem? If we plot the function of the probability of reaching the red state in dependence of x, then we get such a straight line here. I mean, it's just the probability is x. And so here it's actually not a problem, but it is a problem in this Markov chain. And in general, it can be a problem for any cyclic Markov chain, because this solution function is only semi-continuous. And that means that for any value of x except for 0 and 1, or in this case, except for 0, the probability of reaching the red state is 1. If I flip coins long enough, I will eventually flip heads, except if the probability to flip heads is 0, then I will never flip heads. This is what is happening here. And that's the root cause for lots of practical trouble and practical assumptions of doing graph preservation. But you can this reduction for ETR completeness already works for simple PMCs which are acyclic. It's not that easy. It's not that hard to clarify that graph preservation doesn't change anything about the ETR completeness of the problem. So whether you assume that your assignments are graph preserving or not, the problem will be ETR complete. But it's still a good thing to be aware of. And as a last kind of remark, these things they not only exist in theory, they have been put into many practical tools. And they can be roughly split into two areas, whether you care for all the points, whether you want to basically find the problem which is ETR hard, or whether you just want to find one point. If you only want to find one point, then the essential trick is to come up with a method which is very good at guessing the satisfactory point. You guess that point, and then you check whether this point is correct, and that will not give you like strong guarantees on the termination times, but it will work very well in practice, and it will be sound. On the other hand, you need to do some harder reasoning, either on the ETR constructs, either using SMT solvers, or you will need to come up with abstraction techniques that make the problem simpler. And so there's a lot of literature on both of these areas. So if you want to play with these things, that's definitely possible. If you want to do so, feel free to check out our probabilistic model checker Storm, which has been used for all these tool methods, and on which all these methods have been implemented. And I want to finish with some related work, which is necessarily incomplete here, but there's a lot of interesting work. There are various applications that use parameter synthesis. On the other hand, MDPs with small strategies have been independently investigated. And via this connection, I showed you those ideas are often very much related. There's an area of quantitative verification of software product lines. They are doing a lot of work with probabilistic Markov chains and with parametric Markov chains in particular. There's the continuous time Markov chains and parametric versions of that. They have been investigated quite thoroughly. Their notion of interval and constraint MDPs. They are special instances of parametric MDPs. Modal transition systems and infinite state systems, they come back in if you either look at MDPs or if you consider these parameters slightly differently. So this is all definitely related and has inspired some of this work. So I wanted to say that. To conclude future challenges, I think that a really interesting question would be to look at robust strategies. We do have some complexity results on them, but it's not clear. So what is a robust strategy? Basically, you flip around the order of quantification, and we know that with one parameter, the robust version is already NP hard. And with multiple parameters, it's definitely somewhere is co-ETR hard. So it's a different kind of problem, and it would be interesting to understand those problems better. And if anyone has an idea on the complexity of feasibility in PMDPs with one parameter, I would be very much interested in seeing or hearing about that. And finally, parameter synthesis has yielded a lot of new challenges for verification, because much of the more practical methods, they will iteratively call for verification tools to check them, and so you will spend more time on the same model, which means that you can get away with more powerful and more expensive abstraction techniques that you apply as a pre-processing step. So that's definitely something, if you're into abstraction techniques, I think you will be very happy with these kinds of settings. So that's really everything I wanted to say today. I'm very grateful for your time, and if you have any questions, feel free to ask them now or reach out to me later.